Hello class, welcome to another video in the calculus series. So we're looking at a formal definition of limits. So we are wrapping up the unit on limits, and this is an optional lesson, so you can skip over this lesson if you are not interested necessarily in the proof of limits. So if you wanted to prove why a limit is a certain value, things like that, this is just a formal mathematics with proofs. So you could skip this lesson without any consequence really, and without any loss of understanding in calculus content. Then you'll skip over to lesson 8, in which we go over the derivative. We'll have gone over the derivative in lesson 8. But in any case, we're going to go ahead and look at how we would be able to prove the limits that we've looked at so far in the class. All right, so here we are looking at the definition of the limit. So we're going to look at the definition of the two-sided limit, the the normal limit that we are used to, the one-sided limit, infinite limits, and then limits at infinity. And we're going to basically do various examples. So definition of a limit. Let f be a function defined on an open interval, defined everywhere on this open interval, except possibly at c. The reason why it doesn't have to be defined at c is because we're doing the limit as x approaches c. Okay, so for example, let's say this is our curve, and we are looking at, for example, this value, and we'll say that this value is a whole. Let's suppose that that value is a whole at x equals c. And so when we're looking at this interval, let's say we're looking at this portion of the graph, right? That portion of the graph, for example, between A and B. Well, let's just suppose that this interval is open, right? So we're looking at this section of the graph, but we're doing the limit as x approaches c. And so you don't have to have the function being defined at that point to have a limit, right? So this is why they said except possibly at c. It could be defined at c, but it need not be defined at c. Okay, so let L be a real number. So L is going to be the value of the limit, right, that we're going to find. So let's say that this value is, that limit is L there. So if then limit as x approaches c of f of x is equal to L, well, that means that for all, or for every epsilon that is positive, there exists a positive delta such that the distance between x, the x value, and the c, that distance is greater than 0, but it is less than delta. And if that's the case, if the distance between x and the c, that's what this is saying here, is between 0 and delta, then that implies, that's going to mean that we are going to have it so that the function is a certain distance away from L, and it's a distance that is less than epsilon, okay? So it helps if you think of epsilon and delta as distances away. So, so if you think of this as the distance from x to c, so as we're approaching c, right, we're going to have to start at some kind of x value. So, right, so let's say this is an x value here. So let's say this is an x value here, and we're trying to approach c, right? Well, they're saying if the distance from x to c is less than delta, so for example, let's say this is delta right here, or let's say that the distance from c, that this is delta. All right, well then that means that this here must be c minus delta, right? And if this is delta from here to here, then this point must be c plus delta. So if we're looking at this value of x, say somewhere here, they're saying that the distance between x and c is less than this value delta, okay? And it's got to be positive. X can't be at c. Basically, is what it's saying. If x is at c, then this is going to be equal to 0, and we don't want that to be equal to 0. We want it to approach c without ever actually reaching c, okay? That's the idea of the limit right there. So as this happens, so as this entire thing happens for x, well then, if there's a delta, then there has to be a corresponding epsilon, right? So if we go to the graph, well, there has to be a corresponding epsilon such that, let's say, this from here to here is epsilon, right? And then if I go to this portion of the graph, let's say from here to here is epsilon as well. There has to be a corresponding epsilon. Oh, actually, I did it the wrong direction. Sorry, epsilon is over here, not on the x-axis, it's on the y-axis. There has to be a corresponding epsilon. So let's say this is epsilon, and here this is epsilon. So then if we trace this, it's got to be from here to here. Okay, so if there's a delta, then that corresponds to an epsilon, where it's epsilon away from L, right? Where some function, where like if this is the x value, then this has to be f of x, right? And they're saying that f of x is a certain distance away from L. This is L right here. So it's a certain distance away from L, and that distance must be less than epsilon. That is what this is saying, okay? So if this, then this, right? Then this has to happen. If this does not occur, what's in this box, then that means that the limit does not exist, okay? So this has to happen in order to have a limit being defined, okay? So that's what that is. So that's what it means. But how do we actually go about proving it? So we're going to show you that next. All right, so let's look at example 1. So use the formal definition of the limit, and let's go ahead and change our pen here. So use the formal definition of the limit to prove that the limit of 3x minus 1 as x approaches 2 is equal to 5. All right, so when we start this proof, we generally have the same way that we go about starting it and ending it. You know, and the steps are pretty much, the structure is the same, right? And this is how I'm going to start the proof. So I'm always going to start with this. So I'm going to say given epsilon greater than 0. So we're given that epsilon is greater than 0. Epsilon is some kind of positive number. We want to be able to define what delta is. So we're going to say I'm going to write this a little smaller. Let delta equals some number. And our job is to figure out what that number is. Remember that to prove the limit, we have to show that for every epsilon, there exists a delta. Well, if there exists a delta, then we need to figure out what that delta is, right? So we're trying to prove what delta is. But again, we don't know what it is right now. So we're going to kind of work backwards to find delta. So given epsilon greater than 0, let delta be some number, which we'll find out. And I'll put a period here because that's a sentence, but we'll figure out what delta is later. And then for the next sentence, we're going to say, well, then we're going to start saying that if the distance from x to c, remember that, let me just kind of put this off to the side. What we want to show that is if this this is delta. So if this, then that. Okay, so if this, then this guy. Right, so that's what we want to show. So now we're going to say if f of x minus 2, the distance from x to 2, so if absolute value of x minus 2 is less than 0, or is between 0 and delta, okay, then we want to show this. Then we're going to say, okay, well, f of x, let's do this over here. So f of x minus L, well, f of x, what's f of x? This is f of x right here. So let me replace that with my f of x. 3x minus 1 minus my limit L, this is L, my value L, has to be less than epsilon. So we got to go about showing that. So we're going to clean this up. We're going to simplify this. So we get 3x minus 6. All right, and then next I'm going to pull out the 3. If we pull out a 3 out of the absolute value, it's just going to be 3. So we got 3 times the absolute value of x minus 2 equals. All right, so now what we're going to do actually, before I continue, we now matched up with x minus 2 here in this inequality. So remember this is our supposition. So we're supposing that this is true. So we can use it in our proof. So we're going to say that this is less than delta, right? And if that's less than delta, then this product right here has to be less than 3 delta. Okay, where we replaced x minus 2 with delta. All right, well then, remember what we want to show. We want to show that this is equal to epsilon, right? How can that be equal to epsilon? Well, we can now choose our value for delta such that this is epsilon. So we're going to say that delta is epsilon over 3. And now notice that these cancel, and that leaves me with epsilon. And there's the end of the proof. So now we can finish up the proof, now that we kind of worked our way, and say that delta has to be epsilon over 3. And now the entire proof reads complete. Reads and it's complete. So we have our sentences, we have everything filled out, we are done. We've shown that this is less than epsilon. All right, so that takes care of the first proof, and we're going to keep doing this. Give you an idea of how this works. So again, this is f of x, this is L, this is my C value, right? And the proof. So again, starting with what we were saying earlier, given, so we're going to say given epsilon greater than 0, let, and ideally we're going to try to write these with complete sentences, so you know, with the dot period and stuff like that, but sometimes I'll forget it, you know, occasionally, so that's fine. So we're going to say that let delta equals something, and then we'll go ahead and put a period here. If then we're going to say if absolute value of x minus 3 is between 0 and delta, then we're going to go ahead and start showing this. So then what? So then the absolute value of f of x minus L has to be less than epsilon, but we gotta do the work to figure this out. So we're going to pull out the 2, and now we're going to factor x squared minus 9 using difference of squares. Okay, so now that's officially factored. We can notice that we can split this into 2 absolute values. You can take the absolute value of a product, you know, like by splitting it that way. And now we notice that we have the x minus 3 over here, so we can actually replace that with our delta term. Okay, so we're going to say that this is less than 2 times delta times absolute value of x plus 3. So now we have to figure out what we can replace x plus 3 with, right? The absolute value of x plus 3 in terms of a number or something like that. We can't just have a variable there. Okay, we have to have quantities, right, rather than just variables. What we're going to do is we are going to suppose that delta is some number, right? And usually we choose 1, right? So 1 is a good starting value for delta. So we're going to say that, okay, so let's say the delta is equal to the minimum of 2 quantities. Now, usually delta has to be in terms of epsilon, right? But in order to figure out what it is in terms of epsilon, we usually start with, say, 1. Okay, so we're going to say the delta is 1 for now, or, you know, is the minimum between 1 and some number. So we're going to see what it is for 1, and then figure out what x plus 3 can be written in terms of that. Okay, so what we're going to say is, now going back to this inequality, right, we're going to say that delta is 1. Okay, so I'm going to do this off to the side, so not to confuse what I'm doing here with the main part of the proof, right, which it's not. It's just some work for the side, on the side. So we're going to say, okay, well, 0, we know that, and we're going to ignore the 0 part. We're just going to say absolute value of x minus 3 is less than delta. We're just focusing on that part. But we said that delta has to be 1, right? At least minimum between 1 and something else, but we're going to start with the 1. So if it's 1, then we can convert this inequality to x minus 3. We can write it as a compound inequality. It's between -1 and 1, right? If the absolute value is less than 1, then the actual quantity has to be between -1 and 1. And then what we're going to do is we're going to convert this to x plus 3, right? So we got to have it written in terms of x plus 3. So we're going to add 6 to all sides. Remember, if I add 6 to one side, I got to do to all the sides. But adding 6 turns this middle portion into x plus 3. So I got 7 and 5. So x plus 3 is between 5 and 7. And then now we have it in terms of x plus 3. But now we're going to just focus on this part right here and just say that it's less than 7. So we're going to say x plus 3 is less than 7, the absolute value. Okay, so remember that this doesn't really change anything, because if absolute value of x plus 3 is less than 7, then that means x plus 3 is less than 7. That also means that x plus 3 is greater than negative 7, but we stated here that x plus 3 is greater than 5 already. So really, this is more of a restriction, right? But now we're just focusing on the 7 part, and then we're going to use that. So now we can say, okay, this is less than 2 times delta times x plus 3. We can replace that with 7 now. And so now this is equal to 14 delta. And now we're almost there, because now we want to prove that this is epsilon, but the only way to do that is if delta is equal to epsilon over 14. All right, and that gives us epsilon, and that's the end of the proof. Okay, so we've shown that it's less than epsilon. And so now we can say that delta is the minimum between 1 and epsilon over 14. Okay, so delta is some number, right, which could be whichever number is smallest, 1 epsilon over 14 basically. But we found it, we found a delta, a corresponding delta that would give us what we wanted for the proof. Okay, all right, so let's go ahead and take a look at the next one. So example 3. So okay, here's another one. This one's a rational function this time. So let's do the limit of a rational function. All right, so we're going to say given, again starting with our usual, so given epsilon greater than 0, we're going to define, you could say define delta. I usually just say let delta, but you could say define delta equals, so we let delta equal some number. Again, we don't know what that is yet. If absolute value of x minus 8 is between 0 and delta, then we'll go ahead and do that here. Then that means the absolute value of 1 over x minus 5 minus L, and L is 1/3, has to be less than epsilon. But again, we got to find that, we got to prove that. So we're going to say this is equal to, so now we're going to just we're going to combine these fractions together. Again, I'm going to go through this a little fast. I'm assuming that you know how to combine these two fractions for the most part. So we get 3 minus x minus 5 over 3 times x minus 5. All right, and then we're going to clean up the numerator. So this is going to be absolute value of negative quantity x minus 8 over 3 times x minus 5. Okay, so now we're going to pull out this 1/3, actually this negative 1/3. We're going to actually pull that out. But if I pull that out of the absolute value, that turns into 1/3, right? So if I do the absolute value of negative 1/3, that becomes 1/3. So I'm going to pull that out as a 1/3. And then I'm going to split up the numerator and denominator. So I'm going to put the numerator here, x minus 8. And then we got the denominator 1 over x minus 5. And I just do that because I want to isolate the x minus 8, because now we have x minus 8 here. So I want to use the delta on that, okay? So now we can replace that with our delta. So this has to be, in that case, we can say this has to be less than 1/3 times delta, and then 1 over absolute value 1 over x minus 5. Okay, this is the same thing as 1 over absolute value of x minus 5. So we're going to leave it like that. Okay, so now what we need to do, we need to replace x minus 5 with a number or something like that, because we don't want that quantity to just be there, right? So again, let's suppose that delta is 1 and say, okay, this is the minimum between 1 and some quantity. So again, using this inequality and using delta as 1, doing this off to the side, we get absolute value of x minus 8. Again, I'm using this inequality here, but without the 0, because we're not really concerned with the 0 part. We just want the delta part, right? So this is less than delta. And then, okay, so now we're going to convert this to a compound inequality. All right, and then we're going to convert x minus 8 to x minus 5, but the only way to do that is to add 3, right? So we're going to add 3 to both sides here. That turns into 2x minus 5 is between 2 and 4. So we don't want to get ahead of ourselves and start plugging it in right away, because this is 1 over x minus 5. So we want to do the reciprocal of this inequality first before we plug in, all right? So we're going to do the reciprocal of all the sides. But if I do the reciprocal of this, if I do 1 over x minus 5, well, that's going to flip the inequality, right? Because 2 is smaller than 4, but if I flip it, I get 1/2, and 1/2 is greater than 4. So this actually turns into 1/2 is greater than that, which is greater than 1/4. So something to keep in mind is, when you reciprocate, you're flipping the sign, essentially, the inequality. All right, so now we have that 1 over x minus 5 is less than 1/2. That's what we want to use, okay? We want to use the less than inequality, because remember, in our proof we have to have less than to prove that it's less than epsilon, okay? So now we're going to say that we're going to use this part right here, that this is less than 1/2. So now we're going to say this is less than 1/3 delta times 1/2. Well, okay, well then that's equal to 1/6 delta. And we want to show that that's equal to epsilon, so we're going to replace delta with 6 epsilon. And now we got epsilon. So now we've shown that it's less than epsilon. We can finish our proof and say that delta is the minimum of 1 and 6 epsilon. Okay, so hopefully that was helpful and you're able to, kind of follow that for those 3 examples. So now let's look at one-sided limits. So one-sided limits are just it's essentially just half of what we did. So when we did the two-sided limit, we said that we would have to have absolute value of x minus c being between 0 and delta, right? And remember that this is the same thing as saying x minus c is less than, is between negative delta and 0, and x minus c is between 0 and delta. That's what this is saying. That inequality is saying these two, is saying those two things. It's saying that x minus c can't be 0, but it can be between 0 and negative delta or 0 and delta, okay? And so when you do the one-sided limit, you're really just doing one of these two things. This is obviously going to be the left side limit, and this is obviously going to be the right side limit, okay? So this will be the right side, this will be the left side, hence why we got this here, okay? So that's what we have. All right, so hopefully that kind of makes sense, So in that case, and I've shown why the only thing that changes here, everything else is the same except for the fact that the inequality here, the supposition changes, because now we are approaching c from the left side. So x is on the left side and it's approaching c. So that means, of course, we have to have a negative delta here, so that this is c minus delta, and we're starting in between c minus delta and c. We are not approaching it from the right side, only from the left side, hence this inequality, okay? All right, so let's go ahead and so we're going to show you this on here. So in this case, if we use kind of like the same tactic that we had earlier, this does not have to be defined at C, right? Because it's a limit. So let's say this is C here, and so there exists, there exists a delta, right? There exists some kind of delta. Let's say this is delta right here from here to here. Such that, so let's say that's a cutoff. This is negative delta. This is a delta such that if I subtract delta from C, then X is between C minus delta and C, right? And then if I evaluate that X here, right, when that's going to be f of X, well, that's got to be within epsilon of this value L. So in this case, epsilon is from here to here, right? That's got to be within epsilon of the limit, okay? So they're saying f of X minus L is less than epsilon. That's sort of like the picture of what's going on, all right? So, and similarly, we have the right-sided limit, which is the same thing, but on the right side, okay? So in this case, you would have plus delta, so this would be C plus delta. And so you're only looking at the left side, so I'm going to erase, or the right side. So I'm going to erase the left side now. Okay, we got our L. I'm just rewriting that again. We got our delta on the right side. We got X somewhere between C and C plus delta. And if I evaluate that, then that'll give me f of X, for example. And f of X is going to be within, it's going to be smaller than epsilon away from L. So in this case, epsilon is going to be this. From here to here is epsilon. So this is actually L plus epsilon. So f of X is shorter distance than epsilon away from L. Okay, hopefully that makes sense. I know it's takes a while to kind of digest what we mean by the definition, but once you understand it, it starts to make a whole lot of sense. You know, once you kind of start thinking about it. Okay, so let's go ahead and prove example 4. So this one is a radical. So I wanted to put an interesting function in here rather than just polynomials or rationals. So let's do, how would we do a radical? So let's prove this. So again, we're going to start with, you know, the usual, right? Given epsilon greater than 0, let delta equals some quantity. So now this is where we use the inequality for the right side, okay? So we're doing a right-sided limit. So we are going to just remove the absolute value. We're not going to focus on the absolute value. This is going to be what you have for a right-sided limit, where x minus 3 is between 0 and delta. So notice that there's no absolute value there, okay? Again, what this is saying is that if I move the 3 over, that x is between 3 and delta plus 3, okay, and 3 plus delta. Which if you think about it on the number line, if this is 3 and this is 3 plus delta, well then you're approaching 3 from the right side, hence x is to the right of it, between 3 and 3 plus delta. That's exactly what that's saying. Okay, so if x minus 3 is between 0 and delta, then we can go ahead and say that the absolute value of f of x minus L is less than epsilon. We got to show that. So we're going to simplify this. So how do we simplify this? Because there's not really much you can do with that square root. So what you're going to do is you're going to get rid of the square root. Essentially, you're going to, you know, kind of like rationalize it in a way. We're going to multiply by the conjugate, and that will get rid of the square root on you know, one of the sides. When I mean one of the sides, I mean the numerator versus the denominator. So we're going to essentially rationalize or get rid of it, but multiply by the conjugate. So let's take this guy, and we are going to multiply by, and I'm going to show this in a separate step. So I'll show this over here. So multiply this by the conjugate. So same thing, but opposite sign right here in the middle. So the 4 changes sign. And then if we multiply on the top, we must do it on the bottom, because essentially we're just multiplying by 1, so that we're not changing anything if we multiply by 1. Okay, so we got this, and then we are going to, of course, distribute on the top, and that gives us 5x plus 1 minus 16. Okay, I'm assuming you know how to FOIL that and all that stuff, so I'm just gonna leave it at that. Over, and we don't have to do anything to the bottom, just leave it. All right, so again, cleaning this up, we have here, this is equal to, let's do that over here. 1 minus 16 is negative 15. All right, perfect. And now I'm going to pull out the 5 here, and so I have x, absolute value of x minus 3 over here. Let me put this over an entire absolute value over square root 5x plus 1 plus 4. All right, so I didn't do anything. I just pull out the 5 really, and that's it. Well, notice that this is a fraction with a denominator, right? So there's a denominator greater than 1 here. So this number is always going to be less than this number. So I'm going to write it down. If you think about it, this makes sense, because if this has a denominator of 1, well, the greater the denominator, the smaller the number. Well, this number is greater than 1. How do we know it's greater than 1? Well, because the square root has a minimum value of 0, right? The smallest value you can have for the square root is 0 in the real numbers. So 0 plus 4 is 4. So this is always going to be greater than 1, which means that if this is greater than 1, that means the fraction as a whole is smaller than this fraction, and therefore the entire product is smaller. Okay, so we can say that and just get rid of that denominator and say it's less than 5 times absolute value x minus 3. Makes things a lot easier. And now that it's less than this, well, we know that x minus 3 is less than delta, so we can use that here. However, this is an absolute value, so how do I deal with that, right? That's essentially what we want to figure out. Like, how do I deal with that if there's an absolute value there? So in order to tackle this, we're going to quickly talk about what the absolute value means, right? So just off to the side, we know that the absolute value of x minus 3 has to be equal to, it's a piecewise function, it's equal to x minus 3, the original quantity, if x is greater than 3, right? So basically, in other words, if x minus 3 is greater than 0, then it's positive. Then we write it as the original. If x minus 3 is less than 0, meaning x is less than 3, then we write this as the opposite. Okay? So, which one is it? Well, it's got to be this one, because we note that for this interval, let me write the interval down. I'll do it off here to the side. Remember that we're looking at this interval, and so then if you look at it, well, then x has to be between 3 and 3 plus delta, which means x has to be greater than 3, right? So if x is greater than 3, we are looking at this inequality, or we are looking at this step. So we can drop the absolute value and just call it x minus 3, okay? So we're going to say that this is equal to 5 times x minus 3. I put parentheses instead of absolute value. And then we can use this. So this has to be less than delta, 5 times delta. All right, so then this has to be equal to epsilon, or less than epsilon, so we got to set delta equal to epsilon over 5. So then we have epsilon, so now it's less than epsilon. And that's the end of the proof. We're going to finish off by writing that delta is epsilon over 5. Okay, so hopefully that kind of made sense with what we were doing for the proof. Okay. All right, so let's look at next example. So this is a one-sided limit, but a left side limit here. So we're going to go about it the same way, but remember the left side limit has the other inequality. So let's start there. So given epsilon greater than 0, let delta equal some number. Then if, now this is the inequality for the left side. So the left side, you want to say if negative delta, or if x minus 2 is between negative delta and 0. So again, what we're saying is that this is 2, this is negative delta, so then this is 2 minus delta. We want to focus on that. So x is somewhere between those two. So if I move this 2 over, I get 2 minus delta less than x less than 2. So x is between 2 minus delta and 2. That's what we're saying. We're doing it on the left side of 2, the left side of limit. All right, so if that's the case, then again, we want to show that other stuff, right? So we want to show, you know, like we did earlier. So then absolute value, x over x minus 2 minus 2 has to be less than epsilon. So we got to say it's equal to, we're going to clean this up a little bit, combine the fractions. So we get x minus 2 times x minus 2 over x minus 2. We're going to, of course, distribute that. So we get, we're just going to distribute and simplify right away. We'll show the step. So x minus 2x plus 4. And then x minus 2x is negative x. So we got negative x plus 4 over x minus 2. Okay, and remember, and we're gonna note that we can pull, we're gonna pull the negative out of the x plus 4, and we get negative x minus 4 over x minus 2. But remember that we can pull this negative 1, we can take the absolute value of negative 1, and that's just gonna give us 1. And so this basically the negative 1 goes away. So we're going to say that this is equal to absolute value x minus 4. So here, let me write this out. Say absolute value of x minus 4 times 1 over absolute value of x minus 2. Okay? All right, so we know that the absolute value of x minus 2, so we know that x minus 2 is that negative delta situation, right? So we know that much. So we're going to be able to use that for this as well. Oh, I just realized this shouldn't be x minus 2. This should be x minus 4. So let me change this to x minus 4 because we're doing the limit for 4. So my bad. I was looking at this x minus 2 and then made me write that. So it should say x minus 4. Okay, so what we're saying is that this is x minus 4 and this is x minus 4, and so we want to be able to use that here. Okay. All right, so we're going to say that, well, x minus 4 is between negative delta and 0, so then how can we use that? That's what we want to do, right, for this problem. Okay, so in that case, so now what we're going to do, so we remember that, what are we going to replace the x minus 4, the absolute value of x minus 4 with? Well, we're going to replace absolute value of x minus 4 with the opposite of x minus 4. Again, why are we going to do that? Well, remember that we mentioned that the absolute value, let's do this over here off to the side here, the absolute value of x minus 4 is equal to x minus 4 if x is greater than or equal to 4, right? So if the quantity is positive, then it's going to be the original, what's inside the absolute value. But it's going to be the opposite of what's inside if it's negative, right? So in other words, if x is less than 4. Less than 4. Well, we know that x is less than 4 because on this number line, using this inequality, it's less than 4 because we got negative delta is less than x minus 4 is less than 0. Well, then if we solve this, we get 4 minus delta less than x less than 4. So x has to be less than 4 according to this inequality, right? So therefore, this has got to be this case where it's negative. So we're going to replace that with negative. And we're going to say, so the opposite of that, and then times 1 over absolute value of x minus 2. And then we can replace this with, we're going to start replacing the x, oh, well, we don't know yet, just yet. But we're going to replace the x minus 4 with this x minus 4 over here with the delta. But first, we got to take a look at that. So we're going to do that off to the side as well. So doing this off to the side, we see that, okay, well, x minus 4 is greater than negative delta. If I just look at this side right here without the 0, I'm not going to even look at the 0 part. So x minus 4 is greater than negative delta. Well, then that means that if I multiply both sides by negative 1, right? So I multiply this by negative 1, that's going to flip the inequality, right? And that's going to turn it into negative quantity x minus 4 is less than delta. And that's exactly what we have here. So we're going to replace that with less than delta. So we're going to say this is less than delta times 1 over absolute value of x minus 2. Okay, that's what we have. Now I'm going to replace the absolute value of x minus 2 with, we're going to try to, replace that with some number using the inequality, right? So we're going to assume that delta is 1. Remember the minimum stuff. So we're going to assume that delta is the minimum between 1 and some number. And then we're going to, here, let me do this. I'm running out of space here, so I'm going to actually just say, I'm just going to insert it here. So delta is equal to the minimum of 1 and some quantity, okay? And so we're going to start replacing, delta with 1. So we're going to look at this inequality. Again, I'm just doing it off to the side so you don't kind of confuse it with the main proof, right? So we're going to say, all right, negative 1, because we're saying delta is 1, is less than x minus 4 is less than 0. All right? So now keep in mind that if I solve this, well then I get, this is saying that x is between, if I solve this, I said that means that x is between 4 and 3, right? X is somewhere between 4 and 3. And if that's true, then that means I can take away this absolute value and replace it with a regular x minus 2, right? Just regular, because x is greater than 2. So therefore, I can release the absolute value. So I'm going to go ahead and replace this with x minus 2, because if delta is 1, then this is already going to be greater than, okay, than 2. All right, so now in this case, we're going to convert this over to x minus 2. So we're going to add 6 to all the sides. So we get 5 less than x plus 2 less than 6. There you go. Oh, I was supposed to turn it into x minus 2. I'm sorry, not x plus 2. So let me change this up a little bit. So we have to add 2 to all sides instead of 6. So this turns into 1, or x minus 2 is between 1 and 2. And again, we always take the bigger number for the inequality. So x minus 2 is less than 2. And so we can plug that in for here. So we're going to replace that with 2. So we're going to say that this is less than delta times 2. Oh, actually, we want to do the reciprocal. Got ahead of myself there. So again, I'm going to do a little bit of work here, and then we'll be almost done. So we're going to reciprocate this part. So it's going to be 1 over 1. Remember that when you reciprocate, the inequalities flip. 1 over x minus 2 greater than 1 over 2. All right. So again, since I reciprocated this expression, or that inequality rather, the inequalities flip. And so we can see that 1 over x minus 2 is actually less than 1. So this is less than 1. So we can replace this with 1. So this is going to be less than delta times 1. And so that means delta must be equal to epsilon. And that is the end of the proof. So we're going to say that delta is equal to the minimum of 1 and epsilon. End of proof. So that one took a little bit of more thought with the absolute values and stuff. But there you go.
All right, so here we go. Infinite limits. So let f be a function defined on an open interval I, defined everywhere on this open interval except possibly at C, just like usual, right? Now let L be a real number. then the limit of f of x as x approaches c is equal to infinity means that for every m, for all all positive m, there exists a positive delta such that the distance between x and c is between 0 and that delta. And that implies, so if that's the case, then that would imply that the value of f of x is greater than that value m. Okay, so we're going to go ahead and show you what this, what this means. So remember, for infinite limits, the limit does not exist. It actually grows unbounded, so it increases without bound, or it decreases without bound. So in this case, we're looking at the case where it increases without bound. So if we, for example, choose an m, right? So for every m, for all m, so we'll just say, okay, let's say we're looking at this m here, and that's our m value, right? So, and says that there exists, for all m, there exists a delta. So there exists some kind of delta. So this is c right here. And if we introduce a delta, for example, this little delta here, right? Negative delta, and then this is going to be positive delta. So a little bit of space away from C. So then our cutoffs here are, so these are our cutoffs here. Sorry, so here and here, right? So it says for all m, there exists that delta, that little tiny spacing there, such that x is between the negative delta value, which this negative delta value is c minus delta, like that x value, and this x value is c plus delta. And so x is somewhere in between this interval, right? So we'll say that x is somewhere here, right? But actually x can't be at c, right? So maybe I should say x is somewhere here and here, or here and here, right? So such that if I take the value of x and I plug it into the function and I get f of x, so if I take this value here, there exists, that delta such that if there is an f of x in that interval, that would be greater than m. Okay, so it's saying that there's such a delta that if I plug in x into the function, I get a value greater than m. Okay, and then this x value must be smaller than the distance delta away, or the distance from x to c has to be smaller than the distance from delta to c, right? And then if that happens, we get something greater than. So obviously f of x is greater than m here. And the same thing on the other side, we can find an x in this interval, right? There is an x in this interval. And when you do this, it's going to imply that it's greater than m. Now, if you look at this picture, these are tiny delta intervals, right? But what we're just saying is that as we're approaching c, essentially, as we're getting closer to c, this f of x is getting greater and greater. And it's always going to be greater than some cutoff c, m, right? If m were a cutoff, it's going to be above it as we're approaching c. That's essentially what it's trying to say. And then, of course, there's the one-sided version of that, right? And then the left-sided version, the right-sided version. So I basically did both sides on this picture. All right. So if we do this for the negative infinite limit, right, where it's decreasing without bound, is pretty similar for every m less than 0. So we could, of course, define a m that's, of course, negative. So we'll say here, I guess, we can say that, let's say this is m, and this m is less than 0. So negative m. There would exist a delta. So let's say this, we know that this is c here. And we're trying to approach that value, right, from either end. So there would exist some kind of delta. So again, this would be c plus delta. this would be c minus delta, such that such that there's an x in between here and x in this interval that I could pick, and I would find a value, say this is x, I would find a value f of x that's less than m. And then I can, same thing here, of course, because it's a two-sided limit, so it could be on it could be on either side. All right, so that's essentially what we're saying, is that we can find a value here in this interval that will be less than m. And if that's the case, then it's getting smaller and smaller, or it's decreasing and decreasing without bounds. And of course, we have the two-sided, the one-sided limit versions, one on either side, which I drew already. Okay, so let's use this definition. So now remember, we're not using epsilon in this anymore. We're using m delta. So the definition that we're using is n delta for the proof. Okay, so this is sometimes referred as m delta proof. All right, so we want to show that the limit of this is negative infinity. So we're going to go ahead and get started here. So we're going to say given all right, so we're going to say given so now we're not using delta, right? So we're not using epsilon, we're using delta and m. So given m greater than 0, let delta equals some number. Now this number, we're going to want it to be in terms of m, but we're going to figure that out later. Oh, this is going to be less than 0, I'm sorry. M has to be negative because we're looking at this. So we're looking at the situation where we have a cutoff m that's less than 0, right? Because we want it to be negative infinity. Okay, so looking at the negative infinity, m has to be less than 0. So given m less than 0, let delta be some number. If, and this is a one-sided limit, so we're going to use the supposition for the one-sided limit. So if x minus 4 is between negative delta and 0, then we can go ahead and proceed and say that if, or no, then absolute value, or not absolute value, I'm sorry, f of x. So remember the situation was that if this, right, then f of x must be less than m. So that's what we're trying to do. If we can show that, then we can end the proof. So, and f of x is 1 over x minus 4. So then 1 over x minus 4 must be less than m, which we're going to try to show. Well, if you think about it, 1 over x minus 4, we know that x minus 4 is equal to, or is greater than negative delta, right? So if we know from here, so we'll do this off to the side, if we know that x minus 4 is greater than negative delta, according to this, right? Then if we do the reciprocal of that, we would get that this has to be less than negative delta. 1 over negative delta, sorry. Negative 1 over delta. Okay, so remember, if you take the reciprocal, you flip the inequality. So this, this would make sense, all right? So in that case, now it's important to note that this situation works only because we know this only works if x minus 4 is a negative number, right? And like it's not a situation where like x minus 4 is positive and then this number is negative. This number on the right side is negative, because we know that x minus 4 has to be negative because remember, if you look at our interval here, it's less than 0. So we know x minus 4 is already negative. So when we're comparing two negative numbers, if, for example, you have a negative, let's say negative 3, we know that negative 3 is greater than negative 4, for instance, right? And so if I were to reciprocate that, well, then we know that negative 1/3 is going to be less than negative 1/4. So as long as we're dealing with negative numbers on either side, this inequality holds. Obviously, if you have mixed signs, this is where you can run into trouble. So when you're ordering these. Okay, so hopefully that kind of made sense. This is negative 0.33, which is indeed less than negative 0.25. All right, so hopefully that made sense why. Okay, so in that case, we'll go ahead and proceed. So now we said that this is less than negative 1/delta, and so now we're going to try to plug this in. So now that we got 1/x minus 4 here, we can go ahead and plug it in. So this is less than negative 1/delta. And so now we just have to show that negative 1/delta is equal to m. And so what you could do is say that delta is negative 1/m. And then when you do that, well, then the m flips, right? So you'll have negative, this will flip up to the top, and you'll get m, and so that will be the end of the proof. Okay, so we would say delta, so we've shown that it's less than m, which is what we wanted to show, and delta here, let delta equals negative 1/m. Now, just letting you know that delta is not negative here, right? This is negative 1/m, but delta itself is not negative, because m, we said, is negative, right? So m is negative because m is less than 0. So then so that means this expression here has to be positive, right? So it's important that you understand that delta has to be a positive number when you're doing these limits. So delta being positive here makes sense because m is negative. All right, so that is the end. We've showed that it's less than m. All right, so let's take a look at another one. So here we go. Use the formal definition of the limit to prove that the limit as x approaches 2 of this function is positive infinity. So now this time, since this is positive, so we're looking at m greater than 0 for this case. So let's go ahead and try that. So given m greater than 0, let delta equals some quantity, which we'll find later. If, now this is a two-sided limit, a general, the general case, of the limit. So we're going to use the absolute value here. So if the absolute value of x minus 2 is between 0 and that delta, then we can go ahead and then we have to show, so need to show f of x is greater than m. That's what we need to show. So that's exactly what we're going to try to go for. Now f of x is 1/x minus 2 squared. So then 1/x minus 2 squared. Okay, so notice that we have an x minus 2 already. So we can kind of take advantage of that fact. But it's absolute value, right? And we don't have an absolute value in this function. But keep in mind that if we look at this inequality, we see that absolute value x minus 2 is less than delta. We know it's greater than 0, right? But we're just going to focus on the less than delta part. Since this is squared over here, right? If we square this, right, and we say x minus 2 squared, then that's the absolute of that has to be less than delta squared. Okay, so and this makes sense because if a number is less than another number, then squaring the number is still going to be less than the square of the other number. Um, and now, since this is positive, we can just get rid of the absolute value. However, since this is always a positive number because it's squared, it will basically, you don't need the absolute value at that point. So we got x minus 2 squared. We can go ahead and release the absolute value, knowing that this is going to be a positive quantity, right? Because it's being squared. So we can just ignore the absolute value and say that this is less than, and then of course we're going to plug it in, 1 over delta squared. All right. So now we can say it's less than 1 over delta squared. So it is less than a quantity. That's what, but we want it to show, like in this case, I wrote less than, so not less than, sorry. Let's finish this inequality here. So if I do 1 over this, now I'm going to reciprocate. I forgot to reciprocate. I went straight for the proof instead of doing the reciprocal. So we've got to reciprocate this, and if I reciprocate this, it's going to be greater than. There you go. So every time we do the reciprocal, remember it's going to switch the order here. So this is going to be greater than 1 over delta squared. All right, which is good because we wanted to show that it's greater than. So now we can say that m, we can do delta in terms of m, so then delta has to be 1. Well, the only way that this could work is if you have 1 over square root of m in for delta, because then this will turn into 1 over m, and then m would flip. Okay. All right, so then in that case, delta has to be 1 over square root of m. That's an interesting choice for delta, but it's one that we found that would help us show that f of x would be greater than m. All right, so hopefully that made sense. So let's take a look at, we should have another example. Let's see. Okay, so that was two examples for infinite limits. So now let's switch over to definition of limits at infinity. Okay, so let f be a function defined on an open interval, like we usually say, but of course it doesn't have to be defined at c. And then this time, remember, definition of infinites and limits at infinity is when you have that horizontal asymptote. So basically x is going to infinity, and then you're approaching some kind of value. So we're saying that this limit means that for every positive epsilon, there exists a positive n such that x is greater than n. So if x is greater than that n, that would imply that the distance from f of x to f of x and epsilon, this is actually reversed. Goodness gracious. Sorry. So these should actually be reversed here. The distance between f of x and L is less than epsilon. Okay, so then if we are showing the scenario, okay, so let's see what this means. What it's saying is that if you have a value n, right? So let's say this is n. Okay, so n is a vertical line, right? Then what you want to say is, okay, well, if x is greater than n, right? Assuming x is greater than n, so that means you're getting bigger than that value. So we'll say x is going there. So if x is greater than n, then that would imply that, and this is L, this value, this asymptote is L, then the distance between f of x and L, so here, let's say we're looking at this x, well then this is going to be f of x. Well, the distance between f of x and L has to be less than some epsilon, right? So for every epsilon, so let's say we have an epsilon, we defined an epsilon here, right? From L. So then this should be epsilon right here. So then this is L plus epsilon. So for every such epsilon, there is an x such that the function is going to be closer to L than epsilon, right? Than the amount epsilon. Okay, and that's essentially what it's saying. Okay, well then, what if we choose a smaller epsilon, right? So you might be asking yourself, okay, well, this has to work for every epsilon. What if we choose a smaller epsilon? I chose an epsilon like around here, right? Well, what if I chose a smaller epsilon? Well, if that's the case, or even smaller, let's do even smaller. Let's do a very tiny epsilon. An epsilon so tiny it might not even show up on the screen. There you go. So very tiny epsilon. Well, now this f of x is not going to cut it, right? Well, it's saying that x is going to be greater than n, so we could find an x maybe greater than n, maybe here, such that when I look at the function value, it's going to be smaller. It's going to be so close to L, it'll be smaller than that epsilon. So we can always find, for every epsilon that's positive, we can always find an x greater than n such that the distance is smaller. That's what the definition is saying. Okay, so hopefully that made sense. And then, of course, go ahead and switch these as well, because I swapped those two. It should always be less than epsilon, and that's what we're going to try to prove, is that that distance is less than epsilon. Now here is, this is negative infinity, so that means that we would have to show that for every n less than 0. So we can show that as well on this picture. So in this case, so now we're going to look at for every negative n. So we're going to say, okay, so let's look at some negative n. This is n less than 0. All right. So let's say this is positive n, this is negative n, for example. You know, it doesn't really matter. We can ignore the right side of the graph. So we're now x is here, and we're approaching negative infinity. So for every for all epsilon, so if I choose this is L. So again, if I choose this epsilon, right? I'm epsilon away from L. Well, then there exists an x value less than n, such that the function, let's say we choose this x value, such that the function is going to be closer to L than epsilon away. All right, and that's exactly what number 2 is saying. All right, so example 8. So we're gonna show using that, using that proof, or using that definition. So this would be an example of an epsilon-N proof. Okay, so before we did an m-delta proof, right, and that was for infinite limits. Now for limits at infinity, we're looking at an n or an epsilon-N proof. Okay, an epsilon-N proof. So given epsilon greater than 0, and you can tell that we're using epsilon because we have a value for the L. So if you have a value for L, you're going to be using epsilon. If you don't have a value for x, right, because it's infinity, it's approaching infinity, you're using n, right, for that. Okay, so given epsilon greater than 0, let n be equal to some number, which we'll have to find. So remember, we need to show that if x is greater than n, that implies, right, that would show that the absolute value of f of x minus L is less than epsilon. So we need to show that. Okay, so then we're going to say that if x is greater than n, then we're going to go ahead and show that. We're going to go ahead and show this absolute value. So absolute value of 1 over x minus 2 minus L, where L is 0. So let me just ignore the 0 in the next step. And then I'm going to put 1 over absolute value x minus 2, just so that, it looks a little bit more easy to handle without having those large absolute values. Now we know that because we know that since x approaches infinity, right? This is off to the side. Since x approaches infinity, that means we can assume that x is going to be large enough where this here is going to be just x minus 2. It's going to be positive, in other words. So we can ignore the absolute value. We don't need the absolute value here, okay? So we're going to say, okay, 1 over x minus 2, and it's going to be positive. Well, if you look at this, you notice that this, so we know that x is greater than n, right? So if x is greater than n, that means if I plug in n here, if I plug in n into this x, so here, let's show this off to the side. So if x minus 2 is greater than n, well then that implies, or is greater than, so here, let me show the whole thing. So if x is greater than n, then x minus 2 is greater than n minus 2. And then that would imply that 1 over x minus 2 is less than 1 over n minus 2. Okay? Again, if you reciprocate, you flip the order. So that's exactly what we're going to do. We're going to say that this is less than 1 over n minus 2. Okay, so now we showed that it's less than a quantity. So now we're going to express that quantity in terms of epsilon, right? Because we want n now in terms of epsilon, because we wanted to show this. So, okay, well then what does n have to be? Well, n would have to be 2 plus, well, I guess what we could do is we could solve. So let's do this off to the side and say, okay, we need 1 over n minus 2 to be equal to epsilon. So let's solve it. Let's solve for epsilon. So it's going to be 1 over epsilon equals n minus 2, and then add the 2 to both sides. And there you go. So n has to be 2 plus 1 over epsilon. Oh, okay, so let's plug that in here. 2 plus 1 over epsilon. And then let's check to see if that's true. And I'm going to do this on the other side. So I'm going to do it over here. Equals 1 over 2 plus 1 over epsilon minus 2. Okay, we just plugged in n. This is for n, right? So then the 2 cancels, and we're left with 1 over epsilon, and then flip it to get epsilon. Okay, we're done. We've shown that this has to be less than epsilon. All right, and that is the end of the proof. Okay, so these are actually not so bad. I mean, it takes a little bit to do any of these proofs, a little bit of experience, but they're not too bad. Okay, so we showed that that's less than epsilon, so we're done. All right, so now this example, we're looking at a negative limit, or a limit at negative infinity here. So that's going to change our approach. So this time we're going to say that n has to be less than 0 instead of greater than 0. Okay, so in that case, let's go ahead and say given positive epsilon, let n be equal to some quantity. If x is less than n, so x has to be less than n because it's got to be negative. Now we're going to assume that we know that n is less than 0. We know that, remember the definition of the limit, for all n, or for all epsilon greater than 0, there exists an n less than 0. So we're supposing that, right? So according to the definition of the limit, so these are both negative quantities, x and n. But x happens to be less than n, we were supposing. So if that's true, if x is less than n, then we want to show that f of x minus L, the absolute value is less than epsilon. That's what we want to show. Okay, so then in that case, let's do the absolute value of the function minus L, and then we're going to clean this up. So combine the two fractions. Okay, combining them to one common denominator, and then simplifying the numerator. And now we know the absolute value of negative 1/2 is just 1/2. So we're going to just pull that 1/2 out. And we're going to say 1 over absolute value of 2x plus 1. Okay, so again, the 1/2 absolute value of negative 1/2 is just 1/2, so we pulled that out, and we're focusing on the 2x plus 1 now. So we know that since x is less than 0, right? X is approaching negative infinity. So if you recall, this inequality is equal to, it's a piecewise function. It's equal to itself if x is less than negative 1/2. Whatever makes this 0, which is negative 1/2, or if x is greater than or equal to. So whatever makes this 0, which is a half, if x is greater than that number that made it 0, which is negative 1/2, then it's equal to a positive quantity. But if x is less than negative 1/2, this quantity is going to turn negative, right? So then we put a negative there. So that's what we're going to do. We're going to say that this is negative 2x plus 1 because since x is negative infinity, this is going to go definitely in that side, on the left side of negative 1/2. All right, so we're going to say, we're just going to put the negative out there and just call this 1 over 2x plus 1. The negative came from this, but I just pulled the negative up front here. Okay, so now we got that. So now we're going to say, now we're going to try to use the inequality here, this inequality to help us. So we're going to do this off to the side. So first off, we know that x is less than n, right? Which means that 2x, which means that 2x is less than n, which means that 2x plus 1 is less than n, or no, 2x is less than 2n, sorry. Which means that 2x is less than 2n plus 1, right? Because if you multiply both sides by a positive quantity, it doesn't change the inequality. If you add 1 to both sides of the inequality remains unchanged. If you reciprocate, which we're going to do next, then the inequality flips, right? So here, assuming that they're both positive or both negative numbers, which this is true, they're both negative numbers. So this inequality holds true. And then if I multiply by negative 1/2, which because I have this negative 1/2 there, so I'm going to multiply by negative 1/2, that's going to flip the inequality this way. All right, so in other words, this is a less than inequality, which is good because we wanted to show that this is less than epsilon. So we're gonna now replace this with this guy, okay, in terms of n. So we're gonna say that this is less than negative 1/2 times 1 over 2n plus 1. There you go. Now we got it less than. So now that we got it that it's less than, we're gonna do it in terms of epsilon now. And then if we can write that in terms of epsilon, then we're done. So basically, we want this to be negative 2 epsilon. Because if it's equal to negative 2 epsilon, then it will cancel out with the negative 1/2, leaving us with epsilon. Okay, so let's do this work off to the side. All right, so we need this to be equal to negative 2 epsilon. So if I solve that, I'm going to say, okay, well, negative 1 over 2 epsilon equals 2n plus 1. So if I solve for n, I get n equals negative 1/2 times, well, let me just show the entire work. So I'm going to subtract 1, divide by 2. So if I divide by 2, that's a half. So divide by 2, subtract from 1. So I get negative 1 minus 1 over 2 epsilon. And then I'm going to pull the negative out and say negative 1/2 times 1 plus 1 over 2 epsilon. Okay, so that's n. We're going to plug that in now into here. All right, and see if that works. So this is equal to negative 1/2 times 1 over 2 times that entire quantity plus 1. All right, and then we notice that the 2's cancel out here, and then we're going to distribute the negative 1 here. So we get 1 over -1 minus 1 over 2 epsilon plus 1, but then the negative ones and the positive one cancels out. And then this flips, leaving us with negative 2 epsilon. I forgot to write the -1/2 here. So let me put this in brackets, if you will. And this becomes -2 epsilon. All right, and I just kind of showed the work in the inside the bracket just because I didn't want to rewrite the -1/2 again. But now you notice that this cancels out, right? And so that leaves us with -1 times negative epsilon is epsilon. Okay, so we've shown that it's equal to epsilon. All right, so now that we show that it's less than epsilon, we are done with the proof. Okay, so now let's look at infinite limits at infinity, right? So we're going to basically combine the two that we've looked at so far, the infinite limits at infinity and then infinite limits. In other words, infinite limits at infinity. So what's the deal with this? So for this is when you have a limit at infinity that grows without bounds or decreases without bounds. So these are interesting in that sense. So this means, so if I'm doing a limit at negative infinity and the function grows without bounds, meaning infinity, positive infinity, well, we're going to be using the mn definition, right? Of this limit. Okay. Notice that when the things go to infinity, we start using m and n. When they're quantities other than infinity, like actual numbers here, then we switch to epsilon-delta, right? So hopefully you kind of see that pattern. But here, since remember, if x is negative infinity, that x, we use n for the x value, right? So then this has to be less than 0 because x is going to negative infinity. And then because this is positive infinity, that means that m is going greater than 0. Okay, so m is positive. All right, so that's one thing I want you to note. And then, so we know that if x is less than n, because it's negative infinity here, then that's going to imply that it's greater than m, which makes sense because it's going to positive infinity. All right, so you just got to be careful with the signs there. So what this is saying is that for all positive m, there exists an n, right? So for all m, so let's just say that this is m, right? Then there exists, and we're doing the negative infinity. So for all m, there exists an n that is less than 0. So that means we're on this side, right? So such that the function is greater than. So for this m value, for the f of x to be greater than, well then it has to be over here or something like that, right? That it has to be greater than m. Okay, well we're saying that there exists an n such that when x is less than that n, so we're going to say, okay, well let's say this is n over here. Okay, there exists an n such that if x is less than that n, well, this is x, and that value is less than n according to our number axis, then f of x is going to be greater than m, okay? Which we can tell is greater than m because it's above the m line. All right, and that's exactly what it's saying. Is that, there's a cutoff where you can find x where the function at x is greater than the cutoff m. All right, so that's what that's talking about. And then if we look at the second or parts to this, we call them 1a, 1b, and that's because they're both going at infinity, but one is positive infinity, one is negative infinity. So in this case, this is positive infinity, so that means n has to be greater than 0. So in this case, it's just the positive version. So if this were negative n, for instance, or if this were n less than 0, then this would be n greater than 0. So again, same thing. There exists an n such that if x is greater than that n, which x has to be on the right side, the function at x is going to be greater than m. And remember, this is the m line, so f of x is above it. Okay? All right, so hopefully that made sense. So now let's take a look at the second part of it. So this is if you have negative infinity instead of positive infinity for for this actual part right here. So because this is negative infinity, that means that m has to be less than 0. Okay. All right, and because x is negative infinity, or x is approaching negative infinity, then the n has to be less than 0 as well. All right, so again, this is saying that for all m less than 0, so let's say this is m and this is less than 0, there exists an n less than 0, so let's say this is n, such that if x is less than n, meaning to the left of n, there exists a function, or there is a value of the function at f of x, at x, which is f of x, such that f of x is less than m, is below this m line. This is m. All right, which means it's going down to negative infinity. That's what it's saying. Okay. And I'm not going to show the other part, but it's the same thing. It's just a positive version of that. It's on the other side, right? Instead of being the negative side. All right, so that's it. So we're going to go ahead and do a proof involving this. So use the formal definition of the limit to prove that the limit of this polynomial as x approaches infinity is infinity. And we know that's true because this is a parabola. So we know that it's a parabola, and that if x approaches infinity, then this is going to blow up to infinity, right? If it's a parabola, quadratic. But we want to prove that. And these are actually pretty, these proofs look like they would be difficult, but they're actually pretty simple, right? When you actually go about proving them, they're actually pretty simple. So here, or at least this type is. All right, so given m greater than 0, so we want, remember that m, if for all m greater than 0, right? Because this is positive, and since this is positive, we're using n. There exists an n greater than 0. That's what, that's what we're trying to show. So for all for given m is greater than 0, let n equal to some number. And again, we know that we're supposing that n is greater than 0, right? Which is the case. So I'll put this off to the side just in case. I usually haven't written that, but we'll just say that. So if x is less than, or sorry, not less than, greater than n, which is greater than 0. There it is. I put it there. That's where I put it. I forget that this is where I would put greater than 0 in the proof. So we don't have to write it twice. I forget that that's where I put it. So here, we know that n has to be greater than 0, so x has to be positive. So if that's true, then we have to show that f of x, so we need to show f of x is greater than m. All right, so, well, f of x is x squared plus 3x plus 1, and we want to show it's greater than m. But if we know that x is greater than n, right, just off to the side, if x is greater than n, well, that means x squared is greater than n squared. And that also means that x squared plus well, let's make this even easier. So let's make this easier. If we have x squared plus 3x plus 1, well, we know that this is going to be greater than 3x plus 1, right? That makes sense because we're getting rid of the x squared portion, and that only serves to make the function bigger, right? Or to make the value bigger. But this is greater than 3x as well, and that makes sense because 3x plus 1 has to be bigger than 3x. Okay, assuming we're dealing with positive numbers here, which we are because x is greater than 0. And this is great, and 3x has to be greater than x, right? Well then, but we know that x is greater than n, so therefore we can say that this is greater than n. But then we can go ahead and say that then n is equal to m,
So that's exactly what we're going to do. I did this off to the side, but I could have just as well done this on the proof. Okay, so we're just going to do that. I just did off to the side, but let's go ahead and do it on the proof. So this is greater than that, which is greater than 3x, which is greater than x, which is greater than n. And n is equal to m. And so if we let m equals n, then that's the end of the proof. All right, so really not so bad if you think about it that way. All right, so let's look at another one. So limit, okay, so this is, this one's interesting, right? It's a rational. So let's go ahead and prove it. So given m, and this is going to be m is less than 0 because of the negative infinity there. And we know that this is going to be the n, so n is going to be less than 0. So given m less than 0, let n equal something if x is less than n, has to be less than because of that negative infinity, which is less than 0, because we're assuming n is less than 0. Then, all right, so then what we're going to say is, well, x squared over x plus 3 has to be less than x squared over x. If you think about it, that makes sense. A bigger denominator means a smaller fraction. Well, this denominator is bigger than this. So therefore, this fraction as a whole is smaller. All right, well, but we know that this is equal to x, right? X squared over x is x. But we know that x is less than n, right? Because that's our supposition. We suppose that x was less than n. All right, well, there we if we set n equal to m, well, that's the end of the proof. Done. All right, so not too bad. All right, so we showed that this is going to be less than m, which is exactly what we wanted. So now let's look at example 12. Okay, so you can skip this example if you want. This is a challenging limit question, and I say challenging, because and there's a lot of parts to this. So if you, so I put a star by it just so that you are aware of that. We are basically done with the lesson, but I just wanted to show a formal definition using trig limits. Okay, so let's go. We're going to go ahead and start then. So for this, first off, let's go ahead and we know that this is just a regular limit, right? General, two-sided limit. So we're going to use the definition. So given, let me go back. So given, let's change the pen. So given epsilon greater than 0, let delta equals some number. If 0 is less than absolute value, x minus c is less than delta, I'm sorry, I'm getting ahead of myself, less than delta, then we could say absolute value of sine x minus sine c has to be less than epsilon. So we want to show that it's less than epsilon. So for this, now there's not really much you can do if you just look at it as it is. So what we're going to do is we're going to use an identity in trig known as the sum to product identity. So you can look this up. But essentially, I'll just write the identity off to the side and then use it, and then I'm going to erase it just because I want to make sure I have enough room. But here's the identity, is that sine of A minus sine of B
is equal to 2 times cosine, or 2 times the sine of a minus b over 2 and cosine of a plus b over 2. So that's the that's one of the sum to product identities. Of course, this is a difference, so it's a difference to sum, or a difference to product. But that's one of the identities. So we're going to use that here because it's going to be very useful. It's easier to deal with products because of absolute value of products. You can split the absolute values. And so it makes it very useful to have to convert this into a product. So let's go ahead and do that. In that case, we get 2 absolute value of 2 sine of, and in this case, a is x and b is c. So we get x minus c over 2 cosine x plus c over 2. All right, and then so like I said, it's very useful having a product because now I can put the 2 out there and then just focus on the absolute values separately of the sine and the cosine. All right, and we're almost there. So what we need to do is what we know. So first off, let's do a unit circle real quick to kind of give you an idea of where we're going to take this proof. So if we have a unit circle, let me draw that a little bit better. Okay, suppose that that's a unit circle. Okay, so let's say this point on the unit circle, we're going to draw a line to that, and we're basically going to draw a right triangle. So we know that in a unit circle that the x value is cosine and that the y value is sine. So we are going to say that this is sine x. And let's say that this angle is x, right? We're going to say that that angle is x. And of course, this angle being x, I don't want you to, yeah, so this angle is x, and then we're going to say that if this angle is x, then this arc right here, let me use another color for that arc, then this arc right here is equal to x, okay? Because remember that the arc length, right, is equal to, so remember arc length is equal to r theta, right? But theta, the angle is x, so it's equal to rx. But the radius of the unit circle is 1, right? And so that means the arc length is x, okay? So it's the same thing there. And x is in radians, of course, and so that's why it's going to work out that way. All right, so we know that the arc length is x, and we can see from this picture that this sine x has to be less than this red arc, right? So with that in mind, we can say that the absolute value of sine x is less than or equal to the absolute value of x. So we can actually confidently say that. All right. So obviously it's going to be less than x when x is 0 because sine of 0 is equal to 0, right? Otherwise, it's going to be less than or equal to x. Okay, so hopefully that made sense geometrically. Now also we want to note that based off of what we know about cosine, that we know that cosine, just like sine, goes between -1 and 1, right? When you draw the actual cosine. And so we're going to say that the absolute value of cosine of x is less than or equal to 1. Okay, it's always between 1 and -1, so the absolute value is going to be always be less than or equal to 1, right? Basically, it's going to be the absolute value is going to be between 0 and 1 inclusive. But we're just going to use this inequality right here. Okay, so with that in mind, if we combine those results, we get that this is less than or equal to 2 times. Now it's going to be less than or equal to whatever's inside here for the sine, right? Because if we use this, sine of x is less than or equal to x, well then sine of x minus c over 2 is less than or equal to x minus c over 2. So we got x minus c over 2, but we got to do the absolute value. And then cosine of x, this is going to turn into 1, right? So absolute value of 1, which is just 1, right? All right, so then this, notice that the 2's cancel. So then this is equal to absolute value of x minus c. Oh, there you go. There's my x minus c. Now we can actually replace that with the less than delta. So this has to be less than delta. And so if we said that delta is equal to m, or not m, epsilon, that would be the end of the proof. All right, and so we can let delta be epsilon, and that will show that this limit as x approaches c of sine of x is equal to sine of c. So what have we shown here? We've shown that sine of x is continuous everywhere, right? For all c, right? For all real numbers, right? That's what we've shown here for all c here. And so this is very useful because you can use this to prove, for example, the limit as x approaches, for example, pi, or let's say pi over 2 of sine of x is equal to 1, right? Sine of pi over 2 is 1. But we can show that that's the case using this exact, structure, because if we replace 1 with sine of pi over 2, right, which is just 1, this is just saying that you can do a direct substitution. And since we've shown that it's continuous everywhere, we can definitely do this direct substitution. And not only that, but we can replace this sine of c with sine of pi over 2. And the proof would work the exact same way, except instead of using c, you're going to use pi over 2. So hopefully that makes sense for this interesting little proof. All right, that is it for the video and the lesson, guys. I hope you found this video informative. And as usual, I'll see you in the next one.